Hey everyone, this is Mr. here. In this video, we're going to be looking at patterns in the periodic table. So here's an image of the periodic table. You can already see that there's a lot of patterns that we know. So for example, we know a lot of the elements are metals. They're located on the left side of the periodic table, and the ones that are non-metals are on the right side of the periodic table. There are a lot of other trends that are present as well. And one of the first people to recognize this was this guy. About 150 years ago, Dimitri Mendeleev came up with his periodic table, and here's kind of a representation of it. He looked at different elements that haven't yet been discovered. So here's some mystery elements. And he predicted a lot of the properties of these elements. So properties like the density, melting point, and even the atomic mass. So you can see here that for these two elements, he predicted these atomic masses. And then later, a few years later, the elements were discovered, and it was found that this element, we now call germanium, had a mass of around 72 atomic mass units. And scandium had an average atomic mass of around 45, almost right on. So Mendeleev was one of the first people to really recognize patterns. We've seen a lot of these patterns already as well. So here's simply just some Bohr Rutherford diagrams of the first few elements. So you can see here very quickly that patterns are present. We already know that as you're going down the periodic table, we add orbitals. So we have these orbital shells. So first period going across has 1, second has 2, third, 3, etc. We also see patterns in the number of valence or outer electrons. So you can see that group 1 has 1, and all the way down here, group 17 has 7 valency electrons. We've seen lots of patterns before. And we also know patterns in terms of ionic charge. So there's a lot of patterns that we look at, and that's kind of the cool thing about the periodic table. It allows us to predict different properties of elements, and it's a very, very useful tool as a result. So what I have here, I've got a picture. Now these are images of actual atoms. So the first picture here is a representation of the individual carbon atoms in a diamond. And on this side, we've got an image of the individual silicon atoms in a crystal of silicon. Now these pictures were taken using a really cool device called a scanning force electron microscope. This microscope can see individual atoms. It can also move atoms around, which is really cool. It's going to be a lot of interesting potential in the future. So let's look at the size of these. So if you look at these, you'll notice that the size of the atoms in the silicon is a little bit larger than the atoms of the diamond, the carbon atoms in the diamond. And when you look at other experimental data, this is what you see. So this is a representation of the periodic table, and it's almost like a 2D graph where the size of the circle represents the size of the atom. And you can see here that yes, based on other data, silicon is a little bit larger than carbon. And there's some really cool patterns here. So let's look at this. So if you look at the smallest element in the entire periodic table, this little speck here, is going to be helium. And if you look at the opposite end here, francium would be the largest. Well, what the heck is causing this trend? So let's look at the electron configuration, and that's going to help us figure out what's going on, because the size of an atom is really determined by the electrons. So what we have here is, let's look at this. So as I'm going down from helium all the way down to radon and now agneson in the new periodic table, what happens is the size of the atoms gets larger. Why? Well, one pretty obvious thing is that as you're going down, you're going to have more and more orbitals. The other thing, though, is as you're adding more orbitals, the outer electrons are further and further away from the nucleus, which means there's less attraction to the nucleus, there's less pull on them, and they're going to go a little bit further apart. So this kind of makes sense. How about the trend going across? Well, going across, we see that the pattern is that as you're going towards the right, this way here, the atoms get smaller. So we don't change the number or the number of orbitals. They're still the same, but what changes is this. We change the number of protons. So as you're going across, we add an extra proton for each of these as you're going across. And the extra proton in the nucleus means there's more positive charge, and that positive charge pulls on those outer electrons. So those outer electrons are being pulled inwards because of that extra positivity in the nucleus. This is something called effective nuclear charge. Just remember, more positive in the nucleus, sucking those electrons towards the middle. It's like arms pulling in. All right, so that's the pattern for the radius. How about this? So we know that atoms are going to, or most of them are going to gain or lose electrons to become stable. So for example, group 1, they all want to gain one or lose an electron to become positive. Group 2, hey, they want to lose 2 electrons and become 2 positive. And on the other side of the periodic table, we've got fluorine and the halogens, which want to lose 1 electron. So we know that they're going to form ions, but look what happens. What happens is you look at the size of the ions, it's not the same as the size of the neutral atom. Look at lithium here. Lithium and the alkali metals are all smaller. So anytime you're positive, you're smaller. And look at this. The more positive charge you have, the smaller the cation is. It's as if the electrons are being pulled in. Yeah, of course they are, because look what's happening. I've got fewer electrons here, and those fewer electrons have less repulsion, and because of that, they're attracted towards the nucleus more. And the more positive charge you have in an ion, the smaller the radius, because there's more attraction. Now remember, electrons don't like each other, so if you keep adding electrons, what's going to happen is those electrons are going to repel. So let's look at fluorine. If you add an electron, you have extra electrons, they're all repelling each other, and as a result, the fluorine anion is a little bit larger. And the more charge you have, the larger you are. So oxygen is going to be a little bit larger than fluorine because of the extra electrons there. So let's look at the explanation here. So again, if you're a cation, you've lost electrons. You're more positive. And because you're more positive, there's one less energy level. Forgot to mention that earlier. So one less orbital. You've lost an orbital. And also, there's less electrons. So those electrons are being attracted a lot more to the nucleus, and they're being repelled a lot less. Now, if you're going to be an anion, so if you're one of the nonmetals that gain electrons, you're going to have this extra electron. Those extra electrons are going to be repelling each other, and as a result, anions are going to be larger as the electrons are pushing away from each other. And remember, the more charge you have, the bigger the difference. So let's look at the metals. So metals, the more positive charge you have, the fewer electrons and the more attraction there is of the electrons to the nucleus. So you're going to be smaller. Now anions, remember, the more electrons you have, the larger the ion's going to be because there's more repulsion. Just remember, more repulsion here. Here on this side, there's more attraction. So what we're going to be doing in the next video is we'll be looking at other trends. So hopefully you learned something from this video. So you might want to pause, go back, and enter this information on your note.